So this is the review of test 2 that you did. Which of the following pairs are not the same? So let's see. Select one. A, 1A, it says 3-chlorophenol, so which means it's a phenol, an aromatic ring with an OH, and with chlorine on the third carbon over. Carbon bearing the OH is carbon 1. That's 3-chlorophenol. Is that the same as 5-chlorophenol? Let's see. 5-chlorophenol. Okay. 1, 2, 3, 4, 5. These guys are the same. It's just flipping this molecule over. Okay. B2-chlorophenol. Again, OH, chlorine there, and 5-chlorophenol. Obviously, those are not the same because if this is 1, 2, 3, 4, 5, they are not the same. Okay. See, chlorine's next to OH, yet the chlorine's 1 point over. So that's the answer. C, they are the same, and of course, D is the same because this molecule right here, which is 3-chlorophenol, can also be called metachlorophenol. What is the name of the molecule below? So it's a phenol. So this is question 2. I see it's a phenol. And we prioritize the position of the OH as 1. That carbon be 1. And again, prioritize the substituents. You don't want to go the other way. The substituents will have high numbers. Okay, so this has a methyl on here, and you have an ethyl right there. E comes before M, so the name will be 4-ethyl 2-methyl-phenol. That will be the name in here. Okay, 4-ethyl 2-methyl-phenol. Okay, I'm not gonna type it there for the sake of time. Number 3. What is the name of the molecule below? So that molecule has 2 nitro groups, NO2, NO2, and it has a CH3. So obviously, because of the ring with CH3 is called toluene, just like the ring with OH was called phenol. So we'll prioritize this as 1, 2, 3, 4. So this is 3,4-dinitrotoluene. That will be the name for this molecule, 3,4-dinitrotoluene. The answer should have been typed there. Make sure you use hyphens, no spaces. Which of the following substitution deactivates the benzene ring from electrophilic aromatic substitution? So electrophilic aromatic substitution requires that the ring should be electron rich. So to make it electron poor, what do you need? To make it electron poor or to deactivate it, one would need electron withdrawing groups. There was a page in your book, and I think a table that I told you have to know. So from the list electron drawing groups that I see are I see the CN. That's an electron drawing group, so let's assume the ring was here. Okay, this lone pair can be taken out of the ring by resonance, so this is an EWG. That's one of them. Obviously nitro, if you have to write the Lewis structure of nitro, you'll find out that the nitrogen bonded to the ring, let's call it pH, This is just a pH, the ring is a pH. So again, you see it's positively charged, so electrons will be pulled out of the ring, very strongly deactivating. Okay, now OCH3, if you have a ring and you have OCH3 on it, the oxygen has a lone pair. Any element that has a lone pair bound directly to the ring will donate electrons into the ring, activating it, making it electron rich. So this is an EDG. Alkyl group is also an EDG. It donates not by resonance but through bond. Okay, it's through bond. Alkyl groups, R groups donate through bond. So this is an EDG, but it's not as strong. It's moderate electron donating group, EDG. So those two are the answers for question 4. Okay. Review that chapter. I don't know it's chapter what. Is it 4 or 5 on aromatic molecules? Preview it. There's a table there that lists electron donating groups as electron withdrawing groups. You want electron donating groups for electrophilic aromatic substitution. You want electron withdrawing groups for nucleophilic aromatic substitution. Okay, next. What is the product of the following reaction? That reaction is actually called Friedel-Crafts acylation. If you Google this word, you'll see tons and tons of examples of this reaction. So the shortcut is you look at the source of the electrophile, which happens to be the acetyl chloride. I expect the chloride to fall off during the mechanism, and you're gonna have a plus sign. So this is the group that's gonna replace one of the hydrogens on the ring. So in other words, the product here will be, using our shortcut, after identifying our electrophile E+, the ring plays the role of a nucleophile. This electrophile will attach on the nucleophile, losing this hydrogen. That's why it's called electrophilic aromatic substitution. You're gonna substitute the aromatic hydrogen with the electrophile. And that's what you'll get. Okay. So simply put, this ring will attach itself to the carbon as the hydrogen is lost. Okay, so the answer here should be choice, looks like it's choice B, not A. A is an aldehyde, D is a ketone. Okay, it's choice B. Okay, let's see, what do we have? Was that all? Let me clear this so we can use it one more time. Okay, so that was Friedel-Crafts acylation, reactions of aromatic compounds. Question 6. What is the product of the following reaction? This reaction on question 6 is called Friedel-Crafts alkylation. Again, the ring plays the role of a nucleophile. Okay, we are substituting one of the aromatic hydrogens, whichever one. Our source of the electrophile is the alkyl halide. Again, once this falls off, you're going to get a plus charge on that structure. You remember what we call this? Carbocation. That carbocation will replace that hydrogen on the ring. Without going to the mechanism, just using the shortcut, you'll quickly tell that once the hydrogen is gone, the isopropyl carbocation will get attached. So the answer choice here is C. Okay. Next, question 7, that's simply halogenation. If you Google halogenation of benzene or aromatic compounds, you'll see this type of a reaction. So you're either gonna have FCl3 BCl2 or FBr3 Br2. So here the ion trichloride is just it's just a catalyst that helps to break the chlorine apart, such that in real sense, or in summary, the electrophile will be Cl+. All FeCl3 and Cl2 das is to give you the Cl electrophile. So in this case, it's electrophilic aromatic substitution again. So we're gonna substitute the hydrogen with the Cl. So the Cl will sit directly onto the ring. Okay. So you halogenated the ring, so the answer is A. Alright. 8, that's sulfonation reaction. Okay. If you Google the word sulfonation of benzene, you'll find that if you have a ring, one of the hydrogens is gonna be substituted with sulfonic acid. So the SO3 and H eventually will combine in the long mechanism to give you SO3H, which is a sulfonic acid. Okay, so the answer here should be choice C. Okay, moving on. What is the product to the following reaction? So let's see, what reaction do we have? So you already have a CH3 group. We know that that's an electron donating group. Okay, so if you're considering electrophilic aromatic substitution, which is what's happening here, and we know we are sulfonating, the same reagent we used in part 7 is used here. So electron donating groups will direct the group ortho or para. That's what EDGs do. We said R groups are electron donating groups. They donate through bond by inductive effect. So we are adding the same reagent, SO3 in presence of an acid. So the sulfonic acid should end up either ortho or para. Okay. So if you put it ortho, there's gonna be a problem because it's gonna crowd with the methyl group. So the choice we have is to put it on the para position. Ortho is next door to the reference group, which happens to be the methyl. This is the meta position, this is the para, this is meta, this is ortho. So I'm saying if you put this group SO3H right here, it crowds the methyl. So we expect that the product, the dominant product, will have the sulfonic acid on para position. The question wants you to select only one choice, so do not draw the ortho product, because that is unlikely to be formed, and if it's formed, the yield is just gonna be so ridiculously low to be considered. So we would assume the ortho, we just take the para product, and it's para because we know that's an electron donating group, directs the incoming electrophile, para. Okay, next, this time you have a phenol and you have, I think it's still halogenation, but you're bringing Br plus. This cocktail right here just gives you the electrophile Br plus. Now you know that when you have an oxygen or an element with lone pairs that bonded directly to the ring, that's gonna activate the ring. So this is a very strong electron donating group. Again, we expect it to direct ortho para. All right. So there are two possible products formed here, and in fact, arguably, the Br can go everywhere if the bromine reagent is excess. So you can have your bromine on ortho, or it is not a big group. So it's possible to have the bromine on ortho or having it on para if you only added one equivalent of this reagent. But if you add excess, both orthos to the left and right will be substituted, and the opposite position, which is para. Now let's see if we have these two. So this will be the ortho product and this will be your para product. That's meta. This is wrong substituent. This is para. So let's take C. And then yeah, you don't put an ion. So the only answer here is C. We do not have the ortho product listed. So we only go with C because we need to select one product out of the reaction. All right. Next, seems like we have nitric acid and sulfuric acid. Once you see that, you immediately know that you are doing nitration. So let's do the nitration. On question 11, okay, so you have your bromine, okay, and you have your nitric acid and sulfuric acid. So it's a combination, it's a combo of these two acids. I gave you the shortcut at that time when we were learning this. I told you when you see sulfuric acid and nitric acid, the electrophile E plus will be NO2 plus. This reaction is nitration. Now let's go back here. The bromine is a halogen. Halogen are said to be electron withdrawing, but because you have lone pairs, that tends to cancel out the electron withdrawing effect. So generally, would say we'll assume halogens are electron donating. Okay, they're very weakly deactivating. So we assume the ring is still active to react. It's not deactivated. So it's gonna direct, the halogen will direct orthopara, okay? So either there, or there. Now we are nitrating, assuming it's one equivalent because the question did not say excess. So it's one equivalent of our reagent. So we either gonna put our NO2, the electrophile from this cocktail, we're gonna put it either ortho or para. So let's see. If I put it ortho, either to the left or right, I like putting it to the right, then that will be it. If I put it para, let's put it para and see. Is that the farthest down? Yeah. If I put it para, then it's gonna be there. So this will be the para product and this will be the ortho product. What do we have? We're told to select one. So A looks like the para product. No, you're not adding SO4. This is the meta. You're not adding SO4. The answer is A. Okay. Which of the following is chiral? Now, for this one, you had to draw the structures to know. You are looking for a carbon center that has 4 different groups attached to it. So 1,1-dichloro, 5-ethoheptane. So I would draw first the 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. Too much I drew, but I'm gonna leave it that way so that I'll kill one of it and put chlorine. So let's say this is 1, 2, 3, 4, 5, 6, 7. Each corner is a carbon. So I have an etho on carbon 5. I have the 2 chlorines. Okay, that's it. So you see, I know that this one is chiral because, let's see. No, this one is not chiral because if you focus here, do you have 4 different groups? No. That carbon is symmetrical. How do I know? Because I see an etho in red and an etho in black, so to speak. So it has 2 groups that are the same. These 2 guys happen to be the same. You have to have chiral molecule, you have to have at least 1 carbon with 4 different groups. R1 must be different from R2, R2 must be different from R3, R3 must be different from R4, and all throughout those R groups are different. You need 4 different groups. Why? You don't want symmetry. within the molecule. So this point here is symmetrical. Definitely you have two chlorines there, so that one is also symmetrical. So elsewhere on carbon 2, 3, 4, and 7 you at least have two hydrogens. So this molecule is entirely achiral. We're looking for chiral, so A is out. So what about B? Is B chiral? Okay, so let's see. It's the same structure, but now on carbon 5 we have a CH3. Turns out that now this carbon has 4 different groups: the hydrogen, this whole piece to the right, the ethyl, and the methyl. So that point is chiral and makes the entire molecule chiral because there's no symmetry because of that chiral center. So that's one of the choices. So we go to C. It says 1 chloro 5 methyl hexane. I draw my hexane 2, 3, 4, 5, 6. So the chlorine is on carbon 1, 2, 3, 4, 5, and 6. Methyl is on carbon 5, so that's your methyl. This happens to be a methyl anyway, if you have to look at it by itself. So I see the whole molecule does not have carbons with 4 different groups. Carbon 1, 2, 3, 4, all those have CH2s. Okay, so you don't have 4 different groups. Here you have 2 methyls, okay, sharing carbon 5. So again, that's symmetrical, which makes this molecule achiral because there's no carbon having 4 different groups, which is what we're looking for. Okay, so that's not the answer. So next one, D. Let's look at D. It's a heptane 2, 3, 4, 5, 6, 7. And then you have a chlorine on carbon 2. So that's your chlorine on carbon 2. And then a methyl on carbon 6. 1, 2, 3, 4, 5, 6. Methyl on carbon 6. So that's a CH3. It happens that this carbon 2 right here is chiral center because there's 4 different groups. Carbon 3, 4, 5 has 2 hydrogens, so those carbons are each has 2 hydrogens, so those carbons are not chiral centers, they are achiral. And then carbon 6 has a problem because it has 2 methyl groups which are the same, which is symmetrical. So now, because we at least have 1 carbon that is chiral, the whole molecule becomes chiral. Alright, we use the same method to answer question 13. Which of the following is are achiral? So we have to draw cis-1,3 dimethyl cyclohexane. So this is cyclohexane, 1,3 dimethyl, and it's cis. So it means if this is our carbon 1, then on carbon 3 we should also have a methyl. This CH3 here, if I don't show it, you should know that there's CH3. So it says cis, which means same side. You see both of them are away. You can equally draw them towards. Okay, you can equally draw them towards. Either way you look at it, you have internal planar symmetry. You have internal planar symmetry. The top part is reflected down. So these two molecules are achiral. They do have carbons which are chiral centers, which means they have 4 different groups, but overall the molecule has internal planar symmetry, which splits the molecule into half, so it makes the molecule achiral. So A is one of them. Trans dimethyl cyclohexane, trans will be, so that was A, so A is achiral. Trans means that the two metals are not oriented on the same side. So here you cannot have internal plane of symmetry, because if you were to draw the chair, then this one will be up, sorry, this CH3 will be up, okay, that CH3 will be up because this means toward or up, and this will be down, one carbon over, this will be down. So let me use blue, it will be down CH3. So you see, if you try to cut the ring into equal half, there's no way these two metals are reflecting, because one is up and one is down. So this molecule, the trans 1,3-dimethyl-cyclohexene, is overall chiral. We are looking for achiral. Let's look at C. So what of C? It says 1-ethyl 3-methyl-cyclohexane. So we still have a cyclohexane with an ethyl on carbon 1 and a methyl on carbon 3. There's no way you'll have internal plane of symmetry. This molecule will be chiral. See, if you try to cut like this, you have an ethyl on top, a methyl on top, so there's no internal plane of symmetry. So that molecule is chiral. What about D? For D, it says 3,5-dimethyl-cyclohexene. So we draw our cyclohexene, we put a double bond. Let's say this is 1, 2, 3, 4, 5, 6. We number prioritizing the double bond. So you have a methyl on 3. Let's say that's the methyl, and then you have a methyl on 5. That's a methyl. And I can see there's no way I can cut it into equal half, right? Because the double bond will be on one side. So which means this molecule right here is chiral. 1,3-dimethyl-cyclohexene. I mean 3,5-dimethyl-cyclohexene is chiral. It's not achiral, it's chiral. So we only have one answer there. Okay, which of the following choices is an enantiomer of the structure? Enantiomer of the structure. Enantiomer means mirror image. So one had to assign whether it's an RNS. So assigning priorities according to Kern-Ingold rules, oxygen wins. And think we have the hydrogen is group number 4 and is to the back. So whatever answer we get, we keep it. So this will be priority 1, priority 4. And then this long chain will be priority 2. And then the metal will be priority 3. Of course, the long chain is longer than the metal. So looking at the numbers I have, 1, 2, and 3, I'm going counterclockwise. So I'm going S. Right? I'm going S. The smallest group is behind, the two answers an S. So your original molecule is an S. So your enantiomer will be where you have an R. So let's look at choice A. Let's assign chirality for choice A and see if it's an R. So A is out of question because again this one has 1, 2, 3, 4, 5 carbons. This has 4 carbons. A is out. No need to try A. Enantiomers should have the same number of carbons and all elements possible. So this one, 1, 2, 3, 4, 5. Let's try that. We know how to assign our priorities. Oxygen will take 1. This propyl group will take 2, and the methyl will take 3. The smallest group is your hydrogen, is towards you. So the numbers are going 1, 2, and 3. All right. That's an R, but the smallest group is towards you. So 2 assignment is S. So it cannot be choice B because it has same chirality as S as the original molecule in the box. We are looking for an enantiomer which should have an R. Enantiomers are mirror images, so we are looking for the opposite. So if you look at C and assign the hydrogen is away from you. So the oxygen has priority 1, this group will have priority 2, the metal 3, you're going 1, 2, 3, you're going R, which is opposite of S. You have same number of carbons, hydrogens, and oxygen. So the answer here is C. Cannot be D because the OH has been moved over. Okay. I hope you're getting all this chemistry in your head, because your exam will be a hybrid of all these things. Okay, now let's see if question 15. What's the question? Let's scroll down. Which of the following is a diastereomers of the structure below? So diastereomers are one where one point is kept, the other one is switched. So by eyeball, A is this exact same as what you have. B is one of the diastereomers because you see this stereocenter is kept, but the OH is switched. That's what diastereomers means. In diastereomer, at least one chiral center is kept and the other one is switched. Here, both of them are switched. These two are enantiomers. The molecule C and what is in the box are enantiomers. And then D is misplaced because that carbon is this metal is pushed one carbon over. So the only answer I see here is choice B. Alright? Only choice B. Okay. Which of the following the same as what's in the box? So again, we're going to assign chirality and determine by chirality. Same meaning, if the chiral center here is S, what you have here should be S. So let's see what the chirality of the OH center is. So again, oxygen gets 1 based on atomic number, hydrogen 4. The isopropyl will be 2, the metal will be 3. You're going 1, 2, 3. So you're going clockwise. That's an R. We keep the R because the smallest group is away. We are looking for an answer that also has an R. By eyeball, you already see that C is out because it's not looking similar to what we have. Also, similarly, D is out. Let's see, D is out because it looks different. So the answer is between A and B. So let's look at A after eliminating C and D. So if you assign the chirality of this, oxygen will get 1, hydrogen is to the back, gets 4, the metal is 3, the isopropyl is 2, so it's 1, 2, 3. Okay, we are going counterclockwise, that's an S. And we keep the S. So that's an enantiomer. A is the enantiomer of what's in the box because of opposite stereochemistry. So the answer has to be B. Let's verify that. Now, oxygen gets priority 1. Metal we said is priority 3. Isopropyl will be priority 2. So you have 1, 2, and 3. You're going counterclockwise, but the smallest group, which is a hydrogen, is towards you. So true assignment is R. So the answer is B because both of them have same chirality. Okay. And then we are on 17 now. Which of the following is the slowest in SN2 reaction? Other factors kept constant. So you know the rules for SN2. The nucleophile does back attack. So the back side should be accessible. Looking at this, the one that's slowest should be B because if you look at the chair, on the back side is crowded. You do have a metal, you have a CH3 on the back side of this carbon. So if a nucleophile were to come from the back side, it encounters the metal which throws it back out. Of course, with SN2 we say reactivity is metal halide is more reactive than primary, primary is more reactive than secondary, secondary is more reactive than tertiary. In fact, the tertiaries, they don't do SN2 because the backside is crowded, like this is a tertiary. So B is a tertiary, A is primary, C is secondary, D is primary. Okay. Which of the following is the weakest nucleophile in SN2? Other factors kept constant. So you're looking at size. A good nucleophile must not be bulky. So in that case, B is out. Even though it's negatively charged, it's bulky. It's sterically hindered, and then the same problem will be encountered like what we saw here. So B is bulky, is sterically hindered, is huge. So the smaller the nucleophile, the better the nucleophile, and all these have negative charges. So the best choice here of which of the following is the weakest nucleophile is gonna be B because it's bulky. Which one is the strongest? It's gonna be A. Okay, because it's small size at the same time it's negatively charged. Which of the following is a Meso compounds? You are looking for internal plane of symmetry. So the answer here is B because I can split the molecule into equal half. I can split it into equal half, and that's what characterizes Meso compounds. They have stereocenters, chiral centers, but they can split into equal half. So B is one of them. You cannot split A into equal half like I drew the chair before. One metal is up, the other one is down. A cannot be drawn with an internal plane of symmetry. If A cannot do an internal plane of symmetry, C cannot, because A and C are trans. B is C's orientation with the metals. Let's look at D, because it looks like D also has some sort of symmetry. Okay, let's just take this to be a metal, because it is a metal. Right? Is it a metal? Yes, it is a metal. So you see, you can cut this molecule into equal half. All through. The metal has 3 hydrogens. You can cut it equal half. So it's Meso. So the answer is the answer here for Meso is B, structure B, structure D. Okay. On 20. In the reaction below, the concentration of the nucleophile OH is doubled, while the concentration of the electrophile is tripled. What will be the effect? What is the effect of the change in concentration on the SN2 rate? So we said if you double only the, in fact, where I should start is to tell you the rate equation. The rate equation of SN2 equals to rate constant K, which is determined in the lab experimentally, times the concentration of the nucleophile times the concentration of the electrophile. So the nucleophile for you is OH minus. Your electrophile for you is the alkyl halide. That's what being attacked by the nucleophile. So it's an electrophile. So, okay. So if you double the concentration of the nucleophile and triple the concentration of the electrophile, what happens? You multiply 2 by 3, you get 6. So it increases by a factor of 6. Okay. Which of the following is a nucleophile? Nucleophile should be either neutral or negatively charged. Alkenes are neutral nucleophiles, so 2 is a nucleophile. So the answer is 2. You see, this is positively charged, so that's an electrophile. This is missing one bond to be octet. See, AlCl3. The aluminium is not octet, so it can receive electrons, which means it's an electrophile. Okay, so the best answer is here is the double bond, because if you remember where in exam 1 where you are reacting the double bond with an acid by Markovnikov addition to make a carbocation, okay, you'll get a carbocation. So this plays the role of a nucleophile, this plays the role of an electrophile. Okay. you'll see the alkene plays the role of a nucleophile, this plays the role of an electrophile. So alkenes are nucleophiles. Which of the following is a nucleophile? Yeah, answer is 2. Which of the following is the strongest nucleophile in SN2 reaction? The one that's negatively charged will be the strongest. So answer is B. What is the elimination product from this reaction? Okay, let me create space. We need elimination products. So in elimination, the base takes out the beta hydrogen. So beta hydrogens sit on beta carbons, like this is a beta carbon, that's alpha, this is beta. So you will take out that hydrogen or take out this hydrogen in elimination. Now look at the base. The base is not bulky, so that base can go take a hidden beta hydrogen to give you what we call the Z-self product. You take out that hydrogen, that comes in, this drops off by E2 mechanism, where this is a strong base, E2 requires strong bases. So by doing so, you've made a double bond. Okay, and then the byproduct is ethanol and Br minus. But this is the organic product we need. So the answer is A. What is the substitution product for this reaction? So this is SN2. Obviously the alkyl halide is tertiary, right? The alkyl halide is tertiary. SN2 cannot happen. We are looking for a substitution product. So SN2 cannot happen because this is tertiary. Instead SN1 will happen because for SN1 it prefers tertiary over the rest, because the tertiary will tend to give you a more stable tertiary carbocation. Okay, so you get a tertiary carbocation which is more stable. That's why tertiary is preferred for SN1. And then now your nucleophile can come in. That's why SN1 is unimolecular, because only one molecule determines the rate determining step. So this first step, formation of carbocation, has to happen before the mechanism proceeds. So that's the rate determining step. So your ethanol is now attached. The oxygen has one lone pair and a plus charge. We always finish by proton transfer. Okay, proton transfer. Simply put, another molecule of the alcohol can come in to take out the extra hydrogen, and you get your product. Okay, you get your product, which is an ether. In that case, you will have started with an alkyl halide. You move from alkyl halide to make an ether. So the product here is B and C, because this ethanol can attack from the bottom or it can attack from the top. That's why you see the OET with different configurations. Here I just put generally a bond, but it can be away or towards, depending on how the ethanol attacks the carbocation. Okay, and lastly, the alkene below has E configuration. Is that true? This is isomerism of alkenes. So you have your alkene right there. To assign configuration, easy. You cut the double bond into 2, and then you use Kern-Ingold rules. Okay, so here you have a carbon bond directly to the double bond. You have a chlorine. Chlorine has atomic number what? Is it 35? So chlorine. Think chlorine has atomic number of 17. So this has high priority over the carbon, which has atomic number 6. Okay, so priority 1 on the left, this will be priority 2. Priority 1 on the right, priority 2 on the right. Here obviously the ethyl is bigger than the methyl. The ethyl will get priority 1, the methyl will get priority 2. So see, the 1s and the 2s are opposite, so it's an E. So it's true, the alkene has an E configuration. Again, the process is to just look at the elements bonded directly to the carbon and check the atomic numbers in the periodic table. Whoever wins in atomic number gets priority 1. Here you have to find a tie. If this carbon is written here, okay, it's bound moving forward to 3 hydrogens, so I drop the hydrogens. Now, if this carbon is written here, moving forward is first joined to a carbon here, which is the methyl, and then 2 hydrogens. So there's a tiebreaker here. Hydrogen atomic 1, carbon atomic 6. So this carbon wins. This carbon wins, which means this whole group wins. That's why I give it priority 1, that priority 2. So the 1s are opposite, the 2s are opposites. It's E configuration. And that finishes the review of exam 2, which covers most of the concepts in those chapters. Looking forward for exam 3 review.